Welcome to the 6th video in the Math Node series, and today we're finally going to be looking at vector math. So we get it under converter and then vector math. And to demonstrate I'm going to also add in a separate XYZ and a converter math node. Now let's just duplicate these and then add in another combine XYZ. You can plug this into there, this into there. Sorry. And this into there. So this is basically what this node does. It takes in the first vector and then these three values are these three values. And then it combines them back into another vector. And the same goes for subtract, multiply, divide. Now this, when it says here, for example, multiply, it says entry-wise multiply. What that means is for each entry, it's going to multiply the first entry by the first entry, the second entry by the second entry, and the third entry by the third entry. This is not real vector multiplication. Vector multiplication, there are two kinds, and I'll show you in just a minute. And then we have floor, ceiling, modulo, fraction, absolute, minimum, and maximum. They do exactly the same thing as changing all of these to floor, ceiling, modulo, and so forth. So these ones aren't really that interesting. They're useful, but there's really nothing new there. But the ones that are different are the cross product, project, reflect, dot product, and so on. So let's first take a look at these four here. What the distance does, it gets the distance between two vectors, and it's going to take the Euclidean distance. So what it's going to do, it's going to subtract the two vectors, then square each of the components. So we get the first value minus the second one squared, the second value minus the second one here squared, and so on. And then it's going to take the square root. And the length does exactly the same thing, except that it doesn't subtract another vector. It just does, it squares the first value, then the second value and the third value, adds them together, and then takes the square root. Then the scale, what it does, it just multiplies each of the three, all of the three components by this scale value. So it's the same as the multiply, but then these values have to be the same. And the normalize, what it does, it takes in a vector and then divides the vector by its length. Now I'm pretty sure if the length were to be 0, it will just give you a vector that is 0. The vector 0, 0, 0, so that we don't get division by 0 errors. Now let's take a look at the cross product, project, reflect, and dot product. So what this diagram represents is the dot product, and as you can see we have, let me change it. We have this vector, so we have this vector that is this way, and we want to find the dot product between A and B. What it does, it projects it onto the other vector and then multiplies the length of B by the length of this projected vector, and that is the result. So what it gives back is not a vector but a length, and I'll show you in a second why this is useful. Another product that we can use is the cross product, and this will give you back a vector. So the dot product gives you a number while the cross product gives you a vector, and the cross product is going to give you a vector that's perpendicular to A and B, and the length of this vector is equal to the area of the parallelogram created between A and B. But if A were to be on the other side of B, this vector would be pointing downwards. And then finally project. So like I said, the dot product projects, but if you want a vector that is projected, what we can do is we first need to make V have exactly length 1. So for example, let's say this is V hat, which has length 1. Then we can take the dot product with U And what this is going to give us is exactly the length of this part of this vector, and then we just multiply our unit 1 vector v by this length to get the projected vector. And finally we have reflect, and what this does, it reflects an incoming vector around the normal to this plane, so it reflects it. And obviously this is going to be the same, the angle of incidence is going to be the same as the angle of reflection. And how can we find this? Again, we can project our d onto n, but since n is so we need to have d times n hat, because we need to normalize it, now multiply by n. But we can also look at the projection onto this line here, and that's going to be exactly d minus and then d times n hat times n hat. And why is that? Because if we add them together, we're supposed to get d, and obviously these two will cancel out. But for the reflected vector, this one is going to be negative, and that's why these two won't cancel out, and we'll get a negative 2, so we'll get d minus 2 times and then the projected vector, and that will be our reflected vector. So we can look at this in Blender as well. So let me just quickly remove all of this and add back our vector math. So let's take, and I'll also add in a color, RGB maybe, yes. So we'll use this as our vector. So let's plug this into here. So let's change this first to dot product, and let's change this to, there we go, and then let's take a look at the result. So it's not that obvious what it does if you just look at it, but if I make this exactly, so red is the x, green is the y, and blue is the z. So this vector represents the y-axis, and so you can see if you project every vector, or if you take the dot product with every vector on the y-axis, we get the y component of that vector. And the same if I were to change this to the x, we get the x component. And if I change this to blue, we get the z component, but since it's a plane, the z is exactly 0. If I were to extrude it into a cube, you would see that the z is not 0. Great, so that's the dot product, but this is just the length. But if you want the vector itself, we can use project, and again this is 0 because a plane has no height. But if you look at the y values now, we can see that it gets a color because it's a vector, and the color is only on the y-axis because we're multiplying exactly by the y. But as I change it, it starts to turn yellow because it's mixing with red, which is the x-axis, and now we only get the x values. And the cross product will give everything in the plane, so everything on this plane will give us vectors that point out of the plane, so perpendicular to the plane, and that's why they are all blue. But the moment we go into the blue side, we get vectors that lie in all three, if I were to go here, it might be more interesting if we look at it. If you look at a cube, let me just give it a material. So for example, if I just change it to blue, you can see that these vectors all lie in the XY plane, because they're only red and yellow. And the same thing if I change it to green, they all lie in the in the XZ plane and so forth. But if I change it in between, we get values that go anywhere in between. And finally, the reflect is going to reflect it as if this were the vector pointing perpendicular, like the normal, pointing out of the surface. It's going to reflect the vector around that vector. Looks a bit weird, but it's not that useful to just look at it like this. It's more useful when you need it in a formula to calculate things like ray marching and stuff like that. And one thing and the last thing we haven't looked at yet is snap. And what snap does, it's not really as useful. It's a bit like floor and ceiling or modulo, and so yes, we can use it to repeat patterns. It might be used in some formulas, but I haven't used it actually. And what it does, it rounds the first value to, like it says here, an integer multiple of the second value less than or equal to a.